I'll continue with ideal gas. The purpose is to find and calculate the heat capacity from knowledge of the energy states. So in order to get the total energy, we need to find the number of particles in each energy state. Right, we have seen that there are many energy states, and many of these could be occupied. So now let me draw a schematic of the energy levels. So these represent energy levels. Let me call that EI, for example. And in each energy level, there might be a number of particles there. Now I'll call that Ni. Right. Now in the case of the ideal gas, there is a feature that will simplify the problem when we try to derive this number of particles in each state. Eventually we will need to use the Lagrange multiplier method to do that. And now this feature of an ideal gas that will greatly simplify the Lagrange multiplier calculation is that the particles in an ideal gas are spread very widely among the energy states and energy levels. Typically, in a sense that there are usually many more energy states than there are particles, so that it could be very unlikely for two particles to ever occupy the same states. Now this is a feature that we are going to use to simplify the Lagrange multiplier calculation. But before that, we should justify this. So in order to determine whether this is indeed the case, we could do that by thinking about two things. Right. Let's think about the average energy of an ideal gas. Now the average energy of an ideal gas is given by the formula 3/2 kBT, which we know from kinetic theory. And right, the other thing that we need to know is the density of states. It's given by Now let's see how this helps. Let's take a look at the graph, the distribution graph for number of particles among the different energies. So the energies this only happens in discrete levels. All right. Now, at each energy state, there will be a certain number of particles. If I sketch a graph, it might look something like this. Right. Now, the average energy of each particle, let's say it's somewhere around there. That's my 3/2 kBt. Now what we could do to compare the number of particles, so that the total number of particles in this distribution would be n. Say n is the total number of particles. What we want to do is to compare this number of particles with the energy states that are available. Now, if we look at all the energy states that are available, there is an infinite number of them. So obviously, that's always more than the number of particles. Okay, and that would not be very meaningful if we compare it this way. Now, what is more meaningful to compare is to compare, for example, a range of energy. So let me say, if I look at this average energy and compare the number of particles within that range with the number of energy states in that range. Now, at higher energies, we know that there's an infinite number of energies, and that this tail end of the distribution would obviously not go all the way to infinity. Right? There wouldn't be a particle that with energy going all the way to infinity. So we do know that if we can show that there are a lot more energy states here compared with the number of particles, then the same must be true on the other side. So let's look at this. Now, on this side of the average energy, there are about half the number of particles. Now, that is not exactly true. Right? In fact, we can actually calculate the energy that below which there are exactly half the number of particles, and the answer will be slightly different from the average energy by a small fraction. So for now, for this purpose, I'm just going to say that, right, that there are roughly half the number of particles below that, and I'm then going to compare with the number of energy states below the average energy. And we can find that answer because we have the density of states there. So to find the total number of energy states below that energy, now what we could do is, because the density of states is the number of states per unit energy, we could integrate this number of states from 0 to 3/2 kBt to find the number of states. Or there's another way to do it. We can directly obtain a function for the total number of states below a certain energy by looking again at the picture of the K-space that we have used to derive the density of states in the last lecture. So let me do that. So first I need an expression for the total number of states below a certain energy. Very quickly, that's my K space. So that's, say, Kx, Ky, Kz. Now I have my number of, I have my sphere here with a certain K. So what we could do is to count the number of states below this value of, within this value of K. All I need is to take the volume of this sphere 4/3 pi k cubed, multiplied by 1/8 because we only need to consider the positive k components, and then divide by the volume associated with each point, each allowed set of k components in the k space, right? Because the spacing between the points is pi over a, the volume of a cube associated with each point is pi over a cubed. So this gives us the number of points. Now this is often denoted capital G of k, as opposed to little g, which is used for density of states. Now, with this expression, we can now express it in terms of energy using the relation E equals to h bar squared k squared over 2m. This gives gk, g of E. Now this time, to convert the total number of states, we no longer need the more complicated relation that we had for transforming the density of states from k to epsilon. Since we no longer need to have it is no longer about a number of states per interval of energy of k, all we need to find this total number of states is to re-express k in terms of E and then make the substitution. So the answer is quite straightforward. When you do that, this is what you get. So this is the expression. So as I've said, you can also obtain this by directly integrating the density of states. Right? This is doing it from first principles. So now that we have this expression for the total number of states below a certain energy, we can find the number of states below the average particle energy. So what we had was this. We had this picture energy states, particle number, and we are interested to find the number of states below the average 3/2 kBT, the average particle energy. Right. And we wanted to compare this with the actual number of particles there, which is n/2. So this is the formula that we need to use. We need to substitute the 3/2 kBT into here to find an answer. So to make sure that we can get the information that we need, let's have a look at the terms involved. There is the volume. So we're just going to do a very rough estimate to see if there's any to see if the comparison is obviously different between the two numbers. So let me just assume, say a small box of gas at roughly room temperature, so 300 Kelvin, a small box of say 10 centimeter cube of the gas, and something that would be quite close to an ideal gas would be a noble gas like helium. So a helium gas, and each atom of helium has a relative atomic mass of 4. Right, and I believe that's about all we need. We have N here, so let me assume that there is 1 mole of a gas here, so that N/2 is just half of the Avogadro constant. Alright? So we have all the numbers that we need. We have the volume, that's the Planck's constant. We have the energy in terms of the temperature, and the temperature is 300 Kelvin. Right, so we have all these numbers that we need, and all we need to do now is to punch the numbers into the calculator or computer. And here are the kind of numbers that we would get. Now I'm just going to write down an order of magnitude figure. You can do a more accurate calculation on your own. So putting in all these numbers, we will end up with a number for the total number of states below average energy of 10 to the power of 30. And the Avogadro constant divided by 2 is roughly 10 to the power of, let's see, 23. Right. I think that should be 29, probably. So these are the kind of orders of magnitudes that we would get when we punch in these numbers. Now if you look at these two, the difference is quite obvious. There are 1 million times more states than there are particles below the average energy of the particles. So we are talking about lots and lots of states, but very few particles among them. Okay, so we are talking about one particle for every 1 million states when we are down here. So that is why it would be very unlikely for two particles to ever occupy the same state. Now, this feature of the ideal gas is what we are going to use. We are going to therefore assume that no two particles would occupy the same state. Right, we are now ready to apply the method of Lagrange multiplier to find the arrangement of atoms of particles among the energy levels, to find the arrangement that is most likely. Let me draw the energy levels again. Right, you already know that there are many energy levels. So the way to approach this problem is to consider a small interval of energy. Let's say d epsilon. And within this small interval, there are a number of energy levels. So let's say this interval of energy is around the energy EI. Okay, so a small interval around EI. There would be a number of particles, right, within, let's say Ni, a number of particles within this interval, and there would be a number of energy states, Gi. So Gi is the number of states, Ni is the number of particles. Now what we need to do now, when there are some particles there, and so on, is to write down an expression for the number of ways to arrange these particles among the energy states. And the way to do it is to look at this picture, alright? Look at this interval here and notice that we see little circles and we see lines. Now think about these as just objects. So we have these objects of circles and lines, and we have Ni of the circles and Gi of the lines. And imagine arranging these circles and lines in different ways. So we have two different types of objects. How many ways are there to arrange them? Well, the answer is the total number of objects, which is Gi plus Ni, total number of objects factorial. So that's always the number of ways to arrange the objects if they are all different. But because Ni of them are identical particles, we must divide by Ni factorial. And Gi of them are identical lines, so divide by Gi. Now notice that this expression is different from what we used when we derived the Boltzmann distribution. Now in that case, we have particles which are in a solid. So those are distinguishable particles, because since they are embedded in a solid, we can tell that one particle from another just by their location. Alright, because they are located in different places, we can know that they are different particles. But in this case, because the particles are moving around in an ideal gas, there is no way to tell between the particles. Alright, if you blink your eye, the particle would move to another place, and when you open your eye again, you can't tell which is which. So in this case, we're dealing with indistinguishable particles. That's why we need a different way to do this, to calculate the number of arrangements. Right, so this group of energy states and particles will have this number of ways of arrangements. Now what we need to do next is to then consider the number of arrangements in all the other intervals. So there are many intervals. This is the ith interval, then we have the I plus 1, I plus 2 and so on, and I minus 1, I minus 2 and so on. So there are many intervals, so each one would have number of arrangements given by an expression like that. So the total number of arrangements for all the possible energy intervals is obtained by multiplying all those expressions together. So I will use this big capital pi to represent a product. I'll write I under it, which means that I should multiply the expression for all the possible i's. And that is the final expression for the number of possible arrangements in this ideal gas. And I'll use the symbol familiar by now, the symbol omega, to represent this number of arrangements. So we have this, and this is the expression that we need to maximize. We need to find Ni. We need to find this number of particles at each interval that will give a maximum arrangements. And there are constraints. The constraints are that the number of particles must be constant and the total energy must be constant. So that's N1, N2 and so on, and that's N1, E1, N1, E2 and so on. Now here, I'm assuming that each of this term here refers to a particular interval rather than a particular energy state. So now we are ready to apply the Lagrange multiplier method. And if you recall, the Lagrange multiplier method means that we should take the number that we want to maximize and we should add these to the constraints. And for each constraint, we need to multiply by an unknown factor called the Lagrange multiplier, which we call lambda 1 for n, I call it lambda 2 for u, just like I did for Boltzmann distribution. And as for Boltzmann distribution, we also know that when we maximize a function, we need to differentiate it, and factorials are very hard to differentiate, but for very large numbers, we can use the Stirling's approximation, which involves taking a logarithm. So we would instead find the maximum for the logarithm of omega. Alright? Because logarithm is an increasing function, so when the logarithm is a maximum, omega would also be a maximum. So it would lead to the same answer. And this then is the Lagrange function. So what we need to do next is to differentiate L with respect to ni, alright, for each I, and then solve for ni, solve for this number, which is what we need in order to calculate the energy, because we already know the energy states just from previous steps. Right, so in order to differentiate this, let's do it term by term. Now those two follows the same way as for Boltzmann distribution, so those are easy. Let me just write it down. If I differentiate n with respect to ni, alright, I would just get 1, because except for the ni, all the other terms different from I will give 0, and for u, when I differentiate with respect to ni, I will get ei. So these are the easy ones. Now the tricky one would be for the omega. So let's see how to deal with that. So, this way. Now this is the part where we make use of the property that the number of states G is much bigger than the number of particles. So we're going to do this. The factorial in the numerator, I'm going to write it out this way, sort of in full. So it will be gi plus ni times the next smaller number and so on. Now I'm going to pick out g plus 1 to write down, followed by gi and then dot 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 all the way until 1. So that's the factorial of gi plus ni. Divide by ni factorial gi factorial. If you look at this, notice that gi factorial is the same as this part, gi minus 1 and so on until 1. Right, so this can cancel and then we are left with this. Now what remains here is here, you see we are going from gi plus 1 all the way until gi plus ni. So there are actually ni terms here. But because the number of states gi is a lot bigger than ni, what I could do is I can just neglect all the ni and the smaller numbers in each term. So what I have, therefore, is I have ni factors of this gi. So I have gi to the power of ni over ni factorial. So this is a lot simpler now, and I can now differentiate this. Oh, first we want to apply Stirling's formula. So Stirling's formula, we first take the log. Okay. If I take the log, then the product becomes a sum. And in this case, I have log of gi to the power of ni, which I can bring down the ni, minus log of the denominator, and in the denominator I have ni factorial, and if I apply Stirling's approximation, I get ni log ni minus ni. So this is what I'll get. So it's getting simpler and simpler, and finally I want to differentiate this with respect to ni. So this is a sum over I. Now if I'm differentiating with respect to a particular I, a particular ni, then all the other terms in this summation will be 0 because they are different. They have different values of, there are different variables from ni. So all I need is to keep this term, and I can now forget about the summation. So if I differentiate this with respect to ni, gi does not change with respect to ni, so that differentiates to 1, and then I get log gi down here. And differentiating that gives, right, that differentiates to 1, I get log n and I, and then I differentiate log ni, that gives ni times 1 over ni, differentiate ni gives a 1. So this is what I get. Now those two cancel, so 1 minus 1 equals to 0. So this is it, it's just log gi minus log ni. Now if I now include all the other terms from the Lagrangian, from the Lagrange function, so the first term in the Lagrange function would be, let me just write out the L again for reference. Right, so L is log of omega plus lambda 1 n plus lambda 2u. So dl by dni is equal to, right, so differentiating that gives this, which is log gi minus log log ni. So that's that. And then differentiating n gives 1. Differentiating u gives gives epsilon I, as we have seen just now. So this is what we have. So now that we have differentiated this, to maximize it, we equate this to 0. And then we can finally solve for ni. Now if you rearrange this, we get log of ni equals to, right, log of gi plus lambda 1 plus lambda 2 ei. And finally, ni is equal to, so we raise this to an exponential, we get gi times exponential of lambda 1 exponential of lambda 2 ei. And we have this. Now if you look at this, it may be familiar from Boltzmann distribution. If you recall from the earlier lecture, we rename this unknown as A, and we have made use of the Boltzmann postulate and an expression for entropy from thermodynamics to show that lambda 2 is in fact minus 1 over kBt. So there we have the full expression for Ni. Let me write this out. Ni equals to gi A exp minus ei over k dt. And surprisingly, we end up with the Boltzmann distribution again. Right. Right. Now I'm going to put it in a form that is easier to work with. If you recall, the Ni there is the number of particles in the energy interval d epsilon. Right? So what I'm going to do now is I'm going to divide both sides by d epsilon. If I do that, gi is the number of states in this energy interval. So if I divide this number of states by the energy interval, I get the density of states, Ge. So that's just that. A exp kBt. Now, and in this case, Ni is the number of particles in the energy interval dE. So I'm going to rename this with NEI. So now we have this expression, and the variable here, energy variable is EI. Now we have used I to help us to keep track of the intervals when we did the Lagrange multiplier calculations. So now that we have done that, there's no need to keep the I anymore, because if you think about it, the EI in this formula just refers to a particular energy. So we can do just as well by leaving out the I and just use the E here to represent a particular energy. So this is where we are. Now just to clarify on the meaning of this, so I will describe this as the number of particles per unit energy. Alright, so it is the number of particles divided by the corresponding interval. That's why you have this per unit energy idea coming in here. And right, we already know how to describe density of states. Now we should look at this Boltzmann distribution part again. and think about it. Think about what it means. So what this means, what this actually means is that is the number of particles in one state at this energy E. Now if you think about it, it makes sense because if you look back at this, the GI there is the number of states. If this Boltzmann distribution is the number of particles in one state, then the number of particles in one state times the number of states must give you the number of states in that energy interval. Alright, so therefore this is what this means. Now later on we would learn about other types of distributions like Fermi Dirac distribution and Bose-Einstein distributions and distributions of phonons and photons. So when we learn those new distributions, we would often use the symbol Fe to represent the number of particles in a state. So in this ideal gas case, this Boltzmann distribution is the part that corresponds to Fe. So this is useful to know because a lot of the ways of managing these three terms is the same for all the other distributions as well. Right. Now that we have an expression for the number of particles, we are ready to find the total energy. Almost ready. So let's plow ahead. Now let's take a leap and go straight to the total energy and see where that gets us. Now, so the total energy would be N1E1 plus N2E2 and so on. Right, but now that we have it in terms of number of states or number of particles per unit energy, we would do it a bit differently. We would consider a particular interval of energy, d epsilon, alright, and I would multiply it by NE. So NE was the number of particles per unit energy, and if I multiply it by dE, I get the number of particles in that interval. And if I want to find the energy in that interval, I would multiply this number of particles by E, which is the energy for each particle. So having found the energy in the total energy in that interval, if I now want to find the total energy of all the intervals, and therefore of all particles, I would integrate it over the full range of energy, which is from 0 to infinity. But the energy doesn't actually go to infinity, it's just that at higher and higher energies, NE here would get smaller and smaller until it becomes quite negligible beyond some very high energies. Right, so we'll take it to infinity and NE will automatically take care of the actual values. So this is what we have. We had an expression for NE just now, so let's plug that in. Right. So that expression was G E times A exp minus E over K bt. And we even know what GE is from the previous formulas. So in principle we can integrate this, except that we do have an unknown, which is A. We don't know what A is. So if we don't know what A is, we can't actually find a definite answer. So we have to sort that out first. And this is how we can find A. If you remember from Boltzmann distribution, we found A by adding together all the distributions for different energies, because the sum should be equal to the total number of particles. So it's the same here. Except that in this case, we are doing it by considering the number of particles in a certain interval of energy. And that number is NE, which is the number density, times dE. Now, I would call this the number of density sometimes, the number density sometimes. Now, it doesn't mean the number density as in the number of particles per unit volume in real space, but it will be the number density in per unit energy, or the number distribution in energy. Right. So this is for a particular interval, and if I sum over all intervals from 0 to infinity, I should get the total number n. Right. So to get this total number, we have to do this integral. So NE is density of states times Boltzmann distribution. And we can actually integrate this. We know the function for GE. So this is GE, and these are the rest, and we have an additional factor of A that we need to worry about. So since A is a constant, I'll take it out. Now this expression, if we can integrate this expression, we can then solve for A. Right. In order to integrate this expression, notice that it is with respect to E, and we have an E there, and we have an E square root there. All the other terms are constants. So let's see how to integrate this. So this is n. I would have n equals to A. Let me take out all the constants. 4 pi mv over h cubed square root of 2m What's left in the integral are square root of e exponential dE. Now that's not an easy integral to do, but for integrals like that, we can often find the answers in something called the table of integrals. Now if you Google for table of integrals, you'll find Wikipedia, a link to a Wikipedia list of integrals, which gives this formula. Let me write this out. Integrate 0 to infinity of x squared e to the minus x squared dx equals to root pi over 4. Now this is actually the formula that we need. If you look at these two, not exactly the same. We have a square root there, but we don't have a square root there. But what we could do is we could compare the two and make a change of variable to see if we can express that in terms of that. So, right, the key is to look at, say, the exponential and compare the argument. So x squared corresponds to e over kbt. So let's make that substitution. So if x squared is equal to e over kbt, then e is equal to kbt x squared, and therefore dE is equal to 2x kbt. Then this integral would become e square root of e would be kbt x squared that would be exp minus x squared, because the argument is x squared, and dE would be this, would be 2x kbt, oh there should be a dx there, dx. This is what it looks like. Now if you compare this now, we have a exponential of minus x squared, same as that. We have a square root of x squared there and an x there, which should give the x squared there. So this becomes, if I take out the constant factors, there's a 2 there, there's a root kbt and a kbt, so it's kbt to the 3 over 2 square root of x squared e to the minus x squared dx. And the limits of integration, when e is 0, x is 0, e is infinity, x is also infinity. So then we have this same expression as in the table of integrals, and we can replace this by square root of 4. So this becomes 2 kbt 3 over 2, oh sorry, by square root of pi over 4. Right. So we can replace this by square root of pi over 4, and this would be this. So this now goes into that, and we have integrated the expression, and now we can solve for a simply by rearranging the expression. And if you remember, that a was what was missing for the integral for the total energy. So without actually writing out the expression in full, I'm now going to just assume that we are ready to find the total energy. So the total energy, if you recall, was given by something that looks very similar to the expression in N. Now it helps if we compare the two expressions. If you recall, N was obtained by taking NE dE for the number of particles in dE and integrating. And total energy was obtained by taking the same, by taking number of particles in dE and multiplying by the energy before integrating. So that gives us the total energy. If I look at these two, and if I already have an expression for N, alright, you see that the only difference is the additional factor of E in the integral. So I can simply rewrite this. So that means that if I insert an E there, an additional factor of E there, this N here becomes U. Alright? So that's just some convenient mathematics there. And now we have a new integral. Alright, instead of just a root half there, we have an additional factor of E. Now, but we have already found A just now from the integral for N. So now A is known and we need to integrate this. And the way to integrate this is very similar to what I did just now for N. We need to look up a formula in the table of integrals. So once again, if you go to Google, search for table of integrals and click on the wiki list of integrals, you will find this integral. This one. So this is the one that we could use, and when you do the proper substitution of variables, you find that you can eventually get this or the main integrating part of this into this form where you can make use of the integral. The rest is mainly rearranging it and doing the algebra. So without going into all the steps, I shall just state the final answer, which is 3 over 2 n kBt. Now if you remember from the last lecture, this is exactly the expression which was given by the kinetic theory of ideal gas. So what we have now done is that we have started from first principles, from the energy levels, and by maximizing the number of arrangements subject to the constraints that number of particles and total energy must be fixed, we have actually derived the correct formula for the total energy. And it seems like a very long way, to do something that could be done much more easily by the good old kinetic theory and Newton's second law. But along the way, we have actually developed ideas about density of states. We've developed ideas about finding number of arrangements for indistinguishable particles. We have gained even more experience in using the Lagrange multiplier methods, and we have learned about how to do these exotic integrals. So it goes a long way to tell us that these basic ideas about statistical mechanics, that we can actually use the energy levels and these microscopic quantities to predict the macroscopic, the thermodynamic quantities like total energy and heat capacities. That this way of using statistical mechanics is actually correct, and potentially we can actually apply this to other systems. And in fact, when we go on to learn about electrons and phonons and photons, we find that we can actually make use of many of these ideas that we have developed here. So we'll stop now.